represents a pre-made database object. It's databases as a service. AWS actually changes the shared responsibility model. Now they're managing the operating system. They're managing patching the data. RDS, you only have to care about the usernames and passwords for the database access accounts and the IP control rules and help with it. I have it up on the screen right now. We can all take a minute to read it together. What is AWS's responsibility for security in the cloud? And what those are now? Okay, this is AWS's responsibility. Managing the facilities that host the servers, managing the people and their clearance to work on those servers, the physical security of the data center, such as all the door locks, badge access, key cards, etc. So those three kind of go together. Basically, one day, if you are a CTO like me, you're going to have to fill out a very long security questionnaire to sign some large client where they're all going to ask you hundreds of questions like, what is your policy for background checking employees who have access to the servers? What is your policy for securing all side doors and entrances and exits to the rooms where the servers are located? When you take that questionnaire, you can answer those questions. AWS's problem, AWS's problem, AWS's problem. Okay, next up, AWS's responsibility is to separate the compute assets and network traffic so that even when two customers are sharing hardware, no customer's data ever crosses lines. Remember in a previous lesson, I think when we were talking about the Cost Explorer, we discussed how you live on shared hardware. Any given Dell individual server may be having part of its CPU work on your code, while another part of its CPU is working on a different AWS customer's code. That's how you hit that virtualization and that economy at scale. But it is AWS's job to make sure that never shall the two meet. Any bit or packet that is intended for your server will never wind up being processed by someone else's server, ever. And then finally, the last part of AWS's responsibility is to accurately enforce the rules that you choose to specify, okay? You are responsible for specifying the access protections you want. But once you have specified them, it is AWS's job to enforce them accurately. Okay, what is your responsibility under the shared responsibility model? First, you have to be accurate in specifying the rules you wish to be enforced, okay? The most important part of the shared responsibility model that falls on you is if you are running servers like general purpose computing, you have to patch the operating systems and software that runs on those servers. For instance, if you are running a Windows EC2, you must install the Windows updates. Amazon is providing the secure hardware to run it on and making sure that your little slice of the Windows server belongs to you, but they are not responsible for patching it or making sure that the Microsoft Exchange server you've chosen to install on it is up to date. It is your responsibility to protect and safeguard customer data. So again, let's hypothetically say that you make an RDS database and you are storing customer data in it. That database is going to be held in a secure facility. That's Amazon's problem. And it's going to respect just your network traffic. That's also Amazon's job to enforce. You are the one who has to say, here are the rules for accessing this database. Only these IPs can access the database. Once you specify those rules, AWS has to enforce that only those IPs can ever. Let's talk about another example. Not endorsed decision for convenience to check a box that says this bucket is public access, all five. .179.3.19 in the world. If somebody needs to make a request of that server, they use the domain name routing system, which is what lets them put google.com into the browser address bar. But the DNS system is like, aha, you're asking for google.com. You must want specific IP address. And then that's where your request goes. CIDR is a way of specifying IP address umbrellas. So it looks like an IP address that ends with zeros with a slash and a number after it. The number after the slash says the last this many bits are wildcard. And you need to remember, of course, that one number is 8 bits. So when you see the phrase 10.10.00.16, what that means is these IP addresses represent all IPs that begin with 10.10, but the last 16 bits, aka the last two numbers, are wildcards, which is another way of saying I am trying to talk about everything from 10.10.00 up through 10.10.255.255. That's as opposed to the example in the next line, which only ends in /8. This represents a much smaller umbrella of IP addresses because only the last number is wildcard, so it represents a range of just 255 possible IP addresses. This takes us to the concept of a VPC, a virtual private cloud. VPCs are very important for working in AWS. A VPC is a private allotment of IP addresses that are internal to your network, within which your traffic is private. It is a way of reserving one of the 3 pre-made classes of internal IPs for your private usage, okay? And so this takes me to the concept of explaining the difference between a public and private IP address. The way it works is that many IP addresses you're used to dealing with are public. There is only one of them in the world. They are assigned to some server somewhere in the United States or in Germany or in China, and they are the only copy of that IP address anywhere. So when your when your request looks up google.com, it gets a single definitive answer of where that request should be routed to the google.com headquarters. Now, there are 3 classifications of private IP addresses that are meant for reuse by actors all over the world in non-public environments. And those are the Class A range, which is 10 dot anything, Class B, which goes 172.116 anything to 172.31 anything, and Class C, which is 192.168 anything to 192.168 255. In order to create privately networked devices, such as a small subpiece of the AWS network where you have one EC2 and it privately routes traffic to another EC2 that's right next to it, you don't want that traffic going out to the internet at large and coming back and re-entering the data center. So you give them private addresses, and inside your network, the server that is 10.10.1.1 can talk straight to the server that is 10.1.2.2. And they are your 10.1.1.1, not anyone else's. So just alone in my home, on my Wi-Fi network, I have this PC and the PC behind me. And to each other, they're 192.168.0.1 and 192.168.0.2. Those are my private addresses. You can also use those private addresses within your AWS. There will be no confusion because my MacBook is never talking inside your AWS network. Now, the subnet is a concept where you break down your VPC's overall umbrella of IP ranges into the IP ranges that are assigned to particular availability zones. And remember, just a few lessons ago, we covered how availability zones are what comprise regions. So you have the US East 2 region, which is where your VPC lives, but then you have to parse out, well, US East 2A gets the 10.10.1.0 chunk, US East 2B gets the 10.10.2.0 chunk, etc. So depending on in which data center the actual piece of hardware that runs your EC2 is operating, it will have an IP address assigned within its subnet. It is useful to know, although it probably won't be on the exam, that the first 4 IP addresses, so the ones ending in .0, .1, .2, and .3, and the final IP address, the one ending in .255, are reserved for various networking purposes inside AWS and won't be assigned to devices you create. Now, within a subnet, you have a network ACL, and this is something you will see on the exam. So a network ACL, I have an example here in the last 3 bullet points, is a set of rules about what protocols and ports are allowed to traverse within that subnet. So a network ACL is made up of precedence-ordered allow and deny statements that say that some kinds of packets can move around on your network and some can't. In this example, I am defining for a given network ACL that in a certain subnet, so maybe my subnet of US East 2A, I am allowing traffic to move around inside that subnet if it is HTTPS traffic that is meant for the IP address ending in .6. It's also allowed if it's SSH traffic for the IP that ends in .6. All other traffic is denied. So HTTPS traffic to my particular server, which I'm assuming here is a web server, and SSHing into that server with my terminal are both allowed to happen. Everything else is disallowed. This is pretty clutch because one of the ways people can compromise servers is by taking actions on ports that you weren't expecting. Now, obviously, today there are all different kinds of attacks with different varieties, but the oldest trick in the book is people used to compromise servers with security vulnerability and then turn them into spam blasting servers, which sending spam happens on port 25, the SMTP port. If I had a server that lived in a subnet with this ACL, that attacker would not be able to spam from my server because those ports go nowhere. Traffic cannot communicate on those ports. A similar concept is the concept of the route table. The route table is also something that each subnet has itself, and it is instructions on where traffic should go based on the IP address it matches. In this example, let's say we have a VPC that covers 10.10.1. anything. We want to tell our route table that when it sees traffic that is meant for a 10.10.1 address, it should be keeping that traffic inside the VPC, local routing. If traffic matches anything else, which the phrase 0000/0 is shorthand for any IP addresses, all wildcard, then it must need to get out to the internet in general. So it's time to leave the VPC and route that traffic to the NAT gateway. Okay, that brings us to the topic of the internet gateway and the NAT gateway. The internet gateway is a 2-way configuration that allows traffic in from the public internet to get inside your VPC and traffic from your VPC to get out to the public internet. If you use it correctly with a route table, you can create publicly accessible resources this way. So let's say we want to make a really nice big server to serve our website, and it's going to have the IP address of such and such, and we're going to make DNS records worldwide that say mysite.com is served by this IP address. Well, that's going to have to live in a VPC that has an internet gateway so that traffic from the public is allowed in and people can route to that IP address and get responses back. That's when you use an internet gateway. This is as opposed to a NAT gateway. A NAT gateway is a one-way virtual appliance that allows traffic from inside the VPC out to the public internet, but does not provide any routing way for traffic from the public internet to go back into the VPC. It's actually a secret EC2 instance. You can think of it as a big proxy server. So when do you use a NAT gateway? A NAT gateway should be used if you're not doing something that's like public web servers. Let's say you have a farm of 100 neural network crunching machine learning machines. They might need to access the internet so that they can go make calls to Wikipedia and scrape the contents of Wikipedia and feed it into your large language model. But there is no reason for Wikipedia to ever be able to call your servers. They are not serving websites. You could only be opening yourself up to trouble by creating pathways that lead from the public internet into your VPC. So in that case, instead of an internet gateway, you would put all your machines in a subnet and then route that subnet with a route table saying any traffic that isn't local goes out to the NAT gateway and proxies through that machine to the internet at large. Finally, I'd like to talk about the concept of an elastic IP. This is real simple. An elastic IP is a public IP address you can requisition that then can be dynamically assigned to different servers. Why would you want to do this? The answer is very straightforward and quite clear. If you're going to make a nice big web server, you're going to tell every DNS server in the world, hey, mysite.com lives at this IP address. That server now has that IP address. If you decide you need a second, bigger server later, it will have a new, different IP address. And you would have to painfully update DNS records, which are unpredictable in how they propagate across the globe and can definitely lead to downtime where your site's name doesn't resolve. You can prevent this by requisitioning an elastic IP before you begin, dynamically associating that IP address with the server in question. And if you ever wanted to replace that server with a different server, you could then make your new server behind the scenes and then detach the IP from the first server and attach that same IP to the second server. You don't have to update your DNS records worldwide. All the IPs resolve to the new server. The last thing you'll need to know is security groups. Security groups are like per system firewalls. So it actually operates very similarly to how a network ACL operates, where you allow traffic on certain ports and protocols while disallowing traffic on other ports and protocols. The difference is that it exists at a different tier. So network ACLs has to do with the packets that move around inside your VPC. Security groups are the last line of defense as it approaches a machine. So before this packet is allowed to reach the EC2, one final check on where it came from and what port it's on. So something that's really common, I'm giving examples to help, make this real. Say you're making an RDS and it's going to be a Postgres RDS. It is a Postgres database server, and you have a limited subset of machines that should ever be allowed to hit that Postgres database server. You would put it in a security group saying that I am limited to this range of IP addresses and only on port 5432. I don't want to be exposed on any other port or from any other source. So if somehow someone ever got in and spun up a malicious device on your network with a different IP address and tried to start connecting to your Postgres on port 25 or something, that all goes nowhere. All right, let's take just a minute to walk through a couple pieces of a VPC. So I think I have a lot of good examples in the US East 2 region. Yeah, so here you can see I defined an entire VPC called Mentoring Demo VPC, and it's the one that begins with OF49. It covers 10.10.anything.anything. Now, over here, I've created some specific subnets. So for the devices that are made in US East 2A, those get 10.10.1 anything. And for the ones in US East 2B, those get 10.10.2 anything. Straightforward enough. If we look here under route tables, I can pick one of those route tables and see what my routes are. So most traffic that begins with 10.10 should be kept local. Other traffic should go to the internet gateway. There is an internet gateway attached to this VPC. I don't have any elastic IPs right now. That's good for my bill because those cost $1 a month last I checked. And I don't have any NAT gateways right now because this VPC is a public VPC. It is hooked up to an internet gateway and it can make two-way connections back and forth to the internet. So those are some basics of VPCs and networking. All right. That completes the chapter. I would like to reaffirm that you will not have to know the details of how many of these things work, but I saw a chance to go into some detail, and it never hurts to learn. The depth of question you will most likely be asked is, which of the following services lets you specify which ports and protocols are allowed to traverse within a VPC? And you would have to know that the answer to that is route tables, not how to configure them or how to make different denies or allows. You just have to know what it is they do. But just to recap, we covered the concept of a CIDR range. We covered VPCs, subnets, route tables, network ACLs, NAT gateways versus internet gateways and what the difference is, elastic IPs, and security groups. Thank you so much for your time. If you have any questions, reach out to me on LinkedIn or Twitter. I'll see you next chapter. Hello, everybody, and welcome back to AWS Certified Cloud Practitioner Bootcamp. I'm your host, Bill Bolden, and this is the chapter on EC2. Like with most chapters, I just want to discuss before I begin the relevance of it to the actual exam. EC2 is easily the most important of all AWS services, right up there with S3 and IAM. But it is one of the only services that the exam will expect you to have more than a passing familiarity with. Like the Certified Cloud Practitioner really is a good starting point for exams. You won't be expected to know the nuts and bolts of what services do, just what it is that they do. But EC2 is so core and crucial to the understanding of AWS in general that it really helps to know a few things about the details of how EC2s work too. So that said, let's first iron out what an EC2 is, right? So I'm not just going to assume that everyone is familiar with the concept of a virtual machine. We're going to define it. What is virtual computing? A virtual machine is an actual piece of hardware, like a real server that exists somewhere plugged in a data center that is pretending to be a different server. One real server can host hundreds of virtual servers this way. Each of them are like little segmented pieces of their own CPU, their own RAM, and their own hard disk. What they're actually doing is all taking turns using the real computer's CPU, RAM, and hard disk. So they have what are called virtual CPUs for executing instructions and virtual RAM for using memory. One of the cool things about a virtual server is because it's actually just a data representation of what an entirely separate computer would look like, including CPU cycles and RAM contents, it can change which piece of hardware it's being serviced by. So virtual computing is a little more reliable than conventional computing, also known as bare metal by contrast, because you can be servicing a given virtual machine with one piece of hardware. That piece of hardware can fail, but the image can go live on a different piece of hardware and continue living and processing instructions and functioning, even though the actual machine that was acting as its host has failed in some way. So if you're familiar with things like VMware, this should not be news to you, but that's a general overview on what I mean when I say virtual computing. So EC2 is the most important AWS service, or I think it's right up there with IAM and S3. It creates virtual servers using what are known as AMIs, Amazon Machine Images, and it allocates to that virtual computer computing resources. The important thing you need to know about EC2 is it's what's called general purpose computing. Because it is making for you a mostly blank template of a server, you can then go on to do anything you want with it. If you provision yourself a Microsoft Windows computer in EC2, you can then go on to install Microsoft Exchange and IIS, or as I unsuccessfully tried to do once, play Blizzard's Overwatch over a VPN. That one didn't go so well. But in any event, general purpose computing also means that you can spin up a Linux machine, which is just a terminal interface without any kind of graphical user interface, and begin using yum or apt-get to install the software packages of your choice, then upload to the server some application code, like the code for a website it should run, and now it can do that. EC2s are whatever you can do on a computer, you can do on an EC2. But there's a caveat. If AWS offers specific thing as a service, then it is more correct, especially for the purposes of the exam, to use that service that is made for that thing specifically, rather than build it from the ground up on an EC2. This is for a couple reasons. First is you should know what all the different Amazon Web Services are and when it is appropriate to use them. But also, remember what I said about the shared responsibility model. It reduces your attack surface and the amount of things you are responsible for to use the appropriate service, rather than create an entire virtual server, which can and may be attacked or compromised or have security flaws that wouldn't be exposed if you had less attack surface, okay? A great example of this is, here's a question I've seen on the exam that says you need to run a new MySQL database. What should you do? And one of the choices is you can make an EC2 and install MySQL server on it, and then that EC2 is now your MySQL server. That's an okay answer, but a better answer is I would make a MySQL RDS, and then I would have a totally encapsulated product that only exposes the MySQL port as its in and out source of vulnerability, instead of a more generalized server, which could be compromised in other ways. Okay, so let's go into more detail on the AMI, the Amazon Machine Image. So just getting some virtual computing cycles and access to some virtual RAM does not a computer make. It needs an operating system. That has always been true. And so there are many choices for operating systems you could use. At Amazon, they're called AMIs, and they are essentially templates or images of the hard drive that your machine will be born with, They tend to be pretty bare bones and only have the necessary features to then give you the point where you could then install more things from there. So there's a special variant called Amazon Linux, which is a version of the CentOS distribution of Linux that is optimized to run on Amazon's hardware. It's very lightweight. It comes with relatively few packages. It's just got the basics of Linux, and then you can start from there and install more software to make the EC2 you desire. Microsoft Windows is another option. It should be noted you don't have to pay to license the Windows. Part of the on-demand cost you pay for that server includes the cost of Microsoft Windows. Recently, they started offering Mac OS, and there are many other Linux distributions to choose from too, like Ubuntu, Red Hat, and SUSE. There are two things that appear on the test that you should know about. There are other, more specific purpose images in what is called the marketplace, which is useful images that are, again, like a starting point, like a template for your server's operating system, that come with convenient things pre-installed. On the marketplace, those are vetted by Amazon. Amazon has reviewed the image to make sure it is safe to use. They also have community images, which are uploaded by users for general consumption. Those are not vetted by Amazon. They are used at your own risk, okay? So a good example of something you might find on the marketplace is a pre-made Barracuda server. That's going to be a Linux machine that you can spin up that's already going to have Barracuda's suite of networking tools installed. Similarly, they have ones for OpenVPN is one I've seen, and I think there's one for Splunk or Loggly that I've used. Meanwhile, in the community, there's a lot of pet projects. If you're looking for something more niche, somebody may already have made an AMI that comes with your favorite large language model pre-installed on it or something. But Amazon hasn't vetted that. So make sure you know what you're doing or you trust the publisher before you spin one of those machines up inside your infrastructure. Okay, now the next thing to understand about EC2s is that they have these names like C4.large or R5.medium. And the pattern for that is class of server, generation of server, size of server, okay? So here's what you need to know. The first letter is the class, which is the family of servers it belongs to. We'll go over the families in a second. The second number is the generation. Higher numbers are newer. So Amazon never takes old generations away for reasons of backwards compatibility. They won't pull the rug out from underneath you like that. But in general, if you have a choice what kind of T you want to run, you should run T3s over T2s. The T3s are newer models. The third word is the size, which is how much of that server you are buying. Each size is double the previous size. A good example is, let me see if I can remember this off the top of my head, a C4.large is 4 CPUs that goes with 8 gigabytes of RAM. A C4.xlarge is 8 CPUs that goes with 16 gigabytes of RAM. So every time you need to double the amount of resources you're consuming, either in terms of CPU power or RAM power, you're going to want the next size up. So what does that first letter mean? Here are some of the most common kinds of servers you will see. M's, I like to think, stands for medium. They're a well-balanced server that has a fair amount of CPU, a fair amount of RAM, and average hard disk input-output. R's are skewed towards giving you a disproportionate amount of RAM with less focus on the CPU for any given size. So if you take any particular size of M and go look at the R of a comparable size, you're going to find much larger amounts of RAM on that server as opposed to the CPU, which is, of course, in contrast to C, which allocates more focus on giving you lots of CPUs without necessarily giving you too much RAM to go with it. G's, which I like to think stands for graphics card, means that on the hardware, there is a actual NVIDIA or AMD graphics processor that your machine will have access to. This is especially important in today's age of both blockchain computing, which needs lots of GPU power, and AI model training, which needs lots of GPU power. The I servers, which I like to think stand for input-output, that's how I remember them, allocate strong hard disk performance along with the other resources. And then the most important kind of server is the T, which, as far as I can tell, doesn't stand for anything, so I have no way to help you remember it. But what a T does is it is burstable. When a T is not using the full CPU power that it has access to, it is saving up extra CPU cycles in what's called a CPU credit balance. Then later, when the server comes under heavier load, it can borrow against its deposits of saved CPU cycles to not go down under the load until it exhausts all the previously saved up cycles. This makes it ideal for web servers, which is a major application to be aware of. Essentially, if I'm running a SaaS business website, and I watch my traffic go bell curve between the hours of 9 and 5 every day, I can use T's, and at 3 a.m. in the morning, when very few people are hitting my website, they are banking most of their CPU cycles in that vault. And then the next day, when they come under heavy usage, those cycles are being drawn upon so that they don't go down under the load. Of course, there are additional things you should do in cases like these, like that's also an excellent use case for auto-scaling groups. We'll get to auto-scaling groups in, I think, 2 chapters. But T's make great web servers. All right, let's take a moment just to walk through the EC2 wizard so I can show you how all the things I've discussed work in practice. Let's go to EC2, and let's use the launch instance wizard. So here's where you give it a name. Now here is where you choose your AMI, the Amazon Machine Image, which they have a quick selector for some of the most commonly used. Browse more AMI, and let's see what's installed on it. Here's a variant of Linux that I personally have not heard of. Palo Alto, a different version of Debian. There, I mentioned Splunk. That's a useful one. Now over here in community, these are not vetted ones we can find. Particular purposes. Let me see if I can find some of the more interesting ones. Perhaps I can search for a specific piece of software, such as, no, not Loggly. Well, how about perhaps a Kubernetes pre-made server? Cool. Now, a lot of these are being provided by AWS. Oh, that's interesting. The tab is use at your own risk. The next step, which is choosing your type of server. So let's stick with Amazon Linux, and let's take a look at some of the different sizes. So let's say we want to make a web server. Well, T3 is a great place to start. So let's see, a T3 2 gigabytes of memory, but with 4 gigabytes of memory to go with them. Then 8 gigabytes, then at X large, you start getting 4 virtual CPUs. So an M5.X large pairs 4 CPUs with 16 gigabytes of memory, whereas an R5.X large pairs 4 CPUs with 32 gigabytes of memory. And a C4.2X large gives you 8 CPUs along with just 15 gigs of memory. So you can see the different allocations. Depending on the things you're going to use your server for, different things, choose which subnet and VPC you want it to be born in. Remember our discussion about it is a thing that has to be instantiated in a specific availability zone because it is in a particular data center. So you have to say which subnet you want it to use. The default security group is you can SSH in, but no other traffic, PS. And then how much storage do you want and what type? There's general purpose solid state. You can even go for old school magnetic storage, like Western digital hardware options that are available to you. Concludes this chapter. Have what we discuss varieties of different operating systems and costs copy of Windows. We talked about option, then size. Hello, everybody, and welcome back to AWS Certified Cloud Practitioner Bootcamp. I'm your host, Bill Bolden, and this chapter is on database as a service. So, as I said in the last chapter, the EC2 chapter, with an EC2, the world is your oyster because you can program it to be whatever you want. However, for many common use cases, AWS offers a pre-packaged that thing as a service that is a more specialized way to accomplish just that specific task while reducing your responsibility under the shared responsibility model as well as your attack vector. The first and most important kind is RDS, the relational database service. This is for SQL-style databases, okay? And as I just said, under the shared responsibility model, you lose out the whole part where it was your job to administer the server's operating system patches and users and groups, etc. Your responsibility shrinks to just protecting the customer data that is stored in the Postgres or MySQL database. So what kind of databases can you make? As I just said, PostgreSQL, MySQL, a variant of MySQL called MariaDB, Microsoft SQL Server, and Oracle, which are not free softwares. But again, like with Windows, you can pay for them via the cost of the server in Amazon rather than having to bring your own license. And they come with a pre-made convenient checkbox for instantiating redundantly across multiple availability zones. So it is so common when making a new Postgres server to be your production database, you want that thing to be up all the time. So you could configure it to go across multiple availability zones with replication and failover status, or you could check the box that says, please set it up that way for me. Huge convenience. Next up is Elasticache, which is the popular key value stores known as Redis or Memcached as a service. The technical term when you're dealing with Elasticache is not servers, but clusters. So you make clusters of Elasticache. And in my experience, Elasticache scales extremely well, despite not technically being serverless. So normally I advise, the serverless services are much more scalable than getting pieces of hardware that do the same thing. However, Elasticache, I have often had my different startups outgrow their servers, and I have never had one of my startups outgrow its Redis Elasticache. A moderately sized Elasticache cluster serving Redis can handle millions and millions of requests very easily. DynamoDB is a NoSQL database, most similar to a Mongo or something like that. It is a serverless service that is called a document database. It's sort of like a key value store, but instead of just storing values under keys by name, you can also actually upload JSON objects, and then every field in that JSON becomes a column in the DynamoDB. Tables are called tables, but rows are called items. So you don't add rows to a DynamoDB table, you add items to it. And these items are, again, just secretly JSON objects. So you upload an item, which is a JavaScript object that says ID is 1, name is Bill, type is person, and DynamoDB now has columns called ID, type, and name. You don't have to manage a schema for it. You don't have to make varchar columns that are X characters wide. You just put in freeform data. Now, do not just leap in to using DynamoDB without taking a separate course on DynamoDB. It is very unintuitive and not like SQL at all, the way indexing works. If you just start using DynamoDB without understanding how the indexing works, you're going to have a bad time when you go to write a where clause or a join clause one day and learn that your entire concept of how it works doesn't apply. So I will personally say, in my own editorializing, that I had to use DynamoDB for different minor tasks at about 3 or 4 startups before finally the 4th or 5th time around, I felt comfortable making a startup whose main primary data store was DynamoDB. I did not feel comfortable the first several times that I would always be able to query it the way I felt natural querying databases. It takes some getting used to. They have a service called Redshift over AWS. That's their data warehousing solution. It comes in servery and serverless flavors. You can use any SQL client to query the data that lives in your data warehouse. And I haven't personally experienced this, but according to the marketing page, it has built-in ML on the data stored within. Would love if you have any experience with that, if it actually lives up to the hype. Let me know, because I'm interested in learning for my own purposes. There are also some really cool databases that won't be on the exam for very specific purposes. I would like to teach you what they are because I think it's extremely neat. Neptune is a graph database, particularly optimized for things like in graph data, like social network graphs. QLDB, or the Quantum Ledger Database, is an immutable ledger-style chronological data store that is append-only. So at QLDB, you do not go back and update old rows. It is for an append-only table that you are always tacking things on to the end of. It makes it very good for audit logs. And Amazon Managed Blockchain is what it sounds like. There are 2 blockchains it supports, Hyperledger Fabric or Ethereum. You can host the blockchain there in your AWS account. All right, let's take a second to step through the RDS wizard. So we can see, here we are in RDS. I'm going to click Create Database. Here are those options I mentioned before. Aurora is sort of like the Amazon Linux of RDSs. It is a MySQL or Postgres variant that has been optimized to run very well at Amazon's hardware. And then, of course, you have Microsoft SQL Server, Oracle, Maria, which I personally have not used. Here is where you say whether you want a dev server, which lends itself well to being a single DB, or a production server, which lends itself very well to being multi-availability zone, which is that reference I made earlier to the checkbox that automatically spreads you across several availability zones for redundancy. You have to set what your initial username and password is for this database. Just like with EC2s, you will pick a size of database, how much database you want to pay for, how much hard drive space you're putting with it. I will note that with the Aurora serverless options, you have unlimited hard drive space. It's pay as you go. Would I like to automatically create an EC2 that has a security group defined where it can connect to this Postgres? Which piece VPC do I want it in? What security groups should have access to it? Should I have a public IP address? I don't think that's generally a good idea. And then more and more advanced options. And then like that, you would have a new database. So that was me showing off some of those examples of how you can create different kinds of RDSs. Shouldn't be too much surprises there. That does it for the chapter on the different databases as a service AWS offers. As always, connect with me on LinkedIn or Twitter if you have further questions, and I will see you next chapter. Hello, everybody, and welcome back to AWS Certified Cloud Practitioner Bootcamp. I'm your host, Bill Bolden, and this chapter is on EC2 advanced serving, particularly load balancers, autoscaling groups, and Elastic Beanstalk. So we've covered EC2s and RDSs. You've got a database to hold your database in. You've got a web server to serve as an API resource to access that database. All good. But you can go a lot deeper than this, and you can make web serving pools that are very robust and fault tolerant using some of these more advanced features. Don't just make one EC2, call it your web server, and call it a day. You will want to embrace autoscaling. Autoscaling creates pools of interchangeable servers based off of a template. So what you do is you configure one server to behave as expected, then save and image that server after you've configured it as a new AMI, and then you can use that AMI to launch new templates in the future. An autoscaling group is a configuration saying that you want a minimum number of servers with this template to be running in these availability zones at any given time. and a maximum number of servers that can be running at any given time. You couple that with what's called a scaling policy, which is where you track a metric using CloudWatch alarms. And that metric, whether it's in the alarm status or not, determines whether you have to make more servers or remove servers, okay? I've referenced this many times earlier, especially when we were talking about the combination of reserved pricing and on-demand pricing, but a typical auto-scaling group might be something like, I need between 2 servers minimum, always 2 minimum because you want to be fault tolerant in different availability zones, but am willing to go up to 8 if the servers come under heavy load. And my metric that tracks the scaling policy will be the average CPU load across the entire pool. If it's under 50%, remove servers until you're down to just 2 servers being alive. If it's over 50%, create a new server off the AMI template, add it to the pool so it can help serve the website. If it's still over 50%, add another new server to the pool, repeat until I have 8. Okay, so why use auto-scaling? The first reason is fault tolerance, resilience, and redundancy, because if one availability zone goes down, you have redundant servers in another availability zone to cover. And each server is individually unremarkable. They're all like clones, so there is no single point of failure. In particular, this has saved my bacon in the past when I have had a server become compromised, because as I mentioned before, when you put these out there with their public IP addresses, they can and will be attacked, and I've been able to just go take that server and sacrifice it. Kill it, it's compromised, it's a lost cause, it's gone. The auto-scaling group will create a new server to take its place. It's also pay-as-you-go pricing at its finest. Auto-scaling is one of the hallmarks of why pay-as-you-go pricing at AWS is great. But let's say you have 4 servers in an auto-scaling group. You can't have 4 different IP addresses all answering to the same domain name in DNS. Well, for that, you need a load balancer. So a load balancer is a configuration that has a single IP address that farms out traffic to any number of individual instances, okay? So that is how you make an auto-scaling group that's 10 servers big, all effectively function behind one facade, such as myapp.com. How it actually works is that when a request arrives in a load balancer, it selects one of the devices in the target group and forwards the request onto that server, receives a response back from that server, and then forwards the response back onto the original requester. So the actual life cycle is, I'm trying to hit mysite.com from my browser window. I actually go to the load balancer. The load balancer is like, server 3, it's your turn. Your CPU usage is low. Your turn to answer the call. It forwards the request onto the actual server 3. Server 3 individually calculates and sends back an HTTP response, and the load balancer then comes back to me on my browser and says, here's the answer. And it all happens behind one smooth facade. There are 3 types of load balancer, and you should know the difference. The first is classic. These only exist for legacy reasons. Once upon a time, AWS offered one kind of load balancer, and that was just called the classic load balancer. Since then, we have 2 more special purpose types of load balancer, and you should always use either application or network. The only reason for someone to still have a classic load balancer is because they haven't updated their configuration in 10 years. And as I said during a previous lesson, AWS won't really yank the rug out from underneath you. They will most often continue supporting the thing indefinitely. But let's talk about the 2 types of load balancer that are good to use, application and network. So application load balancer exists at layer 7 of the OSI model. What that means, the OSI model, I'm not going to go into it in detail, but it's basically 7 different layers of which you can see network traffic, where the lowest layer is where it's literally ones and zeros, bits and bytes. And in layer 7, the highest layer, it has meaning assigned to those bits and bytes, like HTTP requests, headers, payload bodies, etc. An application load balancer forwards traffic at the highest level. So it assumes we're dealing with HTTPS traffic here, and it can inspect and route based on properties like the path, the headers, or the content of the payload. For instance, you could look at an incoming HTTP request, understand it as HTTP, and say, depending on whether it's an image upload request, it goes to an S3 bucket rather than to your server pool. That's the kind of thing an application load balancer can do. A network load balancer is a lower tier. It's closer to the bits and bytes. Because not all traffic is HTTP traffic, you might want to use a network load balancer to load balance other sorts of packets, like UDP or other less often used protocols. So network load balancer, like I said, closer to the bits and bytes, can't analyze HTTP properties because not all traffic is HTTP traffic, but it can handle things like UDP and other low-level protocols. Now let's talk about Elastic Beanstalk. Elastic Beanstalk bundles together some EC2s in an auto-scaling group with a load balancer into one easy service that makes it very simple to deploy web applications. An Elastic Beanstalk isn't actually anything that you couldn't do yourself. You could always configure an auto-scaling group with a load balancer in front of it and EC2s throughout that auto-scaling group. However, it can be laborious and you can do a lot of things wrong. It is nice and easy to upload your zipped application serving bundle to Elastic Beanstalk and say, I want a pool between 2 and 8, go make it so, and it makes the load balancer, configures the auto-scaling group, and manages all the particulars of the EC2s for you forever. It's also pretty good at deploying updates when you update your application version. So it actually doesn't configure the whole system. You don't have to administer details of the EC2 like the OS or the image. You start and end with the Node Express or Python Django or compiled jar package and directory. And it assumes you supplied the web serving parts and it does the rest itself. All right, let's take a look to just walk through what an Elastic Beanstalk looks like so we can put a face to the name of some of these features. We'll make a new application. Name, test Peru. All right, we'll make a new version of the application. Why can't I? Is it because I don't have an environment yet? Yes, let's make a new environment. So we'll make a web server environment, and we'll make an environment for it. It's hosted in a particular domain. We're going to let everything be managed by Elastic Beanstalk, and then you choose which kind of pre-made application it is. Tomcat, Apache, Ruby, Python, etc. We'll use Node.js because it is my favorite and also the best language. Joke. Upload our code and actually upload an entire zipped Express.js application. Then there are these convenient presets I can start from. Keep it to the free tier only, which is going to put you on I think a T2.micro is the free kind of server. A Spot, distributed high availability, of course, that's something you want. High availability that uses a mix of Spot and on-demand, and so on. So those are the kinds of things you can do at Elastic Beanstalk. All right, that concludes the lesson on advanced EC2 serving techniques. Just as a reminder, we talked about auto-scaling groups, which is a minimum and maximum across several availability zones that launches servers off of an AMI template and has a scaling policy saying when it is time to make more servers or remove servers. We talked about load balancers, which farm out traffic to every server in an auto-scaling group, and it supports three kinds: the classic, which you shouldn't use, the application, which is for high-level HTTPS-specific traffic, and the network, which is for lower-level traffic. And we talked about how Elastic Beanstalk will handle it all for you. If you have any questions, reach out to me on LinkedIn or Twitter, and I'll see you next chapter. Hello, everybody, and welcome back to AWS Certified Cloud Practitioner Bootcamp. I'm your host, Bill Bolden, and this is the chapter on S3. It is my opinion that S3 is the absolute most important AWS service, just after understanding IAM and EC2. So S3 stands for the Simple Storage Service, okay? It is unlimited storage, typically of files. You can actually throw any data you want in an S3 bucket, but it is most often files, and it boasts 11 nines of durability. What does durability specifically mean? It means that the data is intact and it matches what you originally put up there, okay? This means that when you add together all the little ways data can get corrupted, like checksums or flipped bits or disk errors or corrupt sectors, you add all that up together, and if you ask for a file back from S3, fewer than one in, I think that's 10 billion times, the file will still be available, okay? Not the same thing as availability, reliability, or high availability. Durability is a distinct concept, but it is really hard to get durability like this from other storage services. It supports multiple tiers of availability. So availability, again, is the percentage of uptime that a service responds. And those different tiers of availability you can ask for are called storage classes. We'll go over the storage classes in a minute. They do show up on the exam from time to time. The basic unit of S3 is called a bucket, and the things in buckets, which are almost always files, are referred to as objects, and those objects are accessed by their key, which is usually their file name. So what I'm trying to say here is you can't go wrong by thinking of S3 buckets as folders that hold lots of files that have file names. But the correct terminology is that they are buckets that hold objects with keys, okay? You put the objects into the buckets, and then you get them later by asking for their key back. Like, I want the object that lives at key Bill's headshot.jpg, and then I will get the object, aka the file, back from the bucket. The first and most popular class of availability you can ask for at S3 is to store items, or sorry, to store your objects. Ha, look at me. You can ask to store your objects in the standard class. It costs 2.4 cents per gigabyte per month as of the time I'm recording this presentation, which is in March of 2023, and it boasts 4 nines of availability. So if you store your items as standard class storage, you're paying 2.4 cents per gig per month, and 99.99% of the time you ask for the item, it will promptly be returned. Remember, it has 11 nines of durability, which means that the item is almost never lost or unavailable or irrecoverable. But when you ask, you may not get it right away, or you may not get it promptly. Most of the time, you still will, and you can generally count on it, but the availability here is different than the durability. That's as opposed to the infrequent access class, which is consistently half the price of standard storage. You lose a 9 of availability, and it is a little slower. So, infrequent access is, as the name implies, a good way to save money on items you don't get very often. Sometimes it might be down, or sometimes it will be slower. It still has the 11 nines of durability that your items are not being lost, but they won't always be there when you ask the way they will with standard storage. The next most important kind of storage at S3 is the Glacier class of storage. It is dramatically cheaper at under a half a penny per gigabyte per month, but the files are not accessible on demand. So there's a technique they're using that I think is called like cold storage or something like that. And the files are not being kept in an accessible place. When you want to get a file, first you put in a request saying what the key you want them to go retrieve from deep storage is. And then within 4 hours, you will get a notification that your item is now ready to be viewed. Because Glacier is so cheap, but also involves multiple steps to get your files back out of it, it has very particular use cases. It is ideal for forever storage, log files, and legacy files. Maybe something you're not allowed to delete for legal reasons, but that you don't really ever expect yourself to access again, or for all your log files from years ago to go to live. And if you ever did need them back, it's been years. You could wait 4 hours to go get the log file from 4 years ago. In the meantime, it's so cheap, it's practically free. There are 2 important features of S3 you should be aware of. You don't have to know how they work, but you need to know that they exist. Life cycles is a configuration you can set up on an S3 bucket that asks for an object's storage class to automatically be changed at certain points in its life. This has a really cool use case. Let's say I am building an Instagram clone app. It's going to be a photo sharing app where people can post photos that their friends can see, and you can scroll back to go further back in time into the past. If I believe that 99% of time, people will just be looking at the most recent photos on their home screen, and very infrequently will they go back into the distant past, I should put my images in a bucket that has a lifecycle policy, saying every time an image arrives, it is born into standard tier storage, but at the 30-day mark of its life, change it to infrequent access storage. This way, all my items at the point in time they're not trending anymore go into the cheaper class, and they might be a little slower to respond, but because people very infrequently go back into the distant history on my Instagram clone, it's not really that big a deal. And as time goes on and more of my items mature into the infrequent access stage, I am saving lots of money. Replication is another feature that automatically copies objects from one bucket into another. And this is good for answering questions about disaster recovery, resilience, fault tolerance, business continuity plans, and other such things where you want to have backup copies of your data. Well, let's take a look at S3 in practice and show off some of these features I just discussed. Boy, I have a lot of buckets. Okay, cool. Let's create a bucket. Testing bucket 1, 2, 3, Billy. You have to choose a region you want it in. Now, this is one of those more generalized services that does not exist at a specific availability zone or a specific data center. It exists at the regional level. So I'll keep my files somewhere in US East 1. I don't know where in US East 1 they are, but they're somewhere in the Virginia region. There are very granular access controls with S3 buckets. We won't go into the details here, but you can specify who owns and has access to those items. Here's a big one. This checkbox is very convenient. I think I mentioned this during an earlier lesson, but one of the most major breaches of the last decade of consumer data was because somebody was, for convenience, storing customer data in an S3 bucket that they had not set up privacy restrictions on. You can deliberately uncheck this box to make public buckets. They are buckets where everything you put in them is available at the URL of S3. In general, you should not be doing that. It has limited applicability for maybe a static assets files for a website bucket, but even then, there are ways you can combine S3 with CloudFront to accomplish that task better. I recommend always keeping this block all public access checkbox on. Like I said, it was either the Equifax or the Capital One breach. I cannot remember which, but in one of those cases, an employee was storing sensitive customer data like bank account files in an S3 bucket, and to access it easily later, they had chosen to just make that S3 bucket public. Someone discovered it, and that was the end of that story. S3 supports versioning, so that if you overwrite a file name, or sorry, an object's key, the previous version of that object can live on forever and be retrieved. Like many features in Amazon, you can encrypt the whole bucket at rest. Now, I'm not going to create a new bucket, but let me go into an existing bucket and show you some of those other properties. There's versioning, there's CloudTrail. Where is it under management? Aha, here we go. Here's where you make the lifecycle rules. So I want a new lifecycle rule, and I would like to move the current version of the object, the newest version, between storage classes. 30 days in, move me to infrequent access. Perfect. And then I could even go further and move it to the even less reliable one zone infrequent access after 60 days, and so on. You can have multiple stages in your lifecycle. And then here's where you create replication rules. show you the options for this. Where's the destination? Where are these files going to? You can actually copy them across AWS accounts entirely. So you could have a distinct account for backup purposes where your files go to live in case of disaster recovery. That takes us up to the end of the chapter on S3. This is one of those services where you don't need to just know what it does. You need to know some details of how it works because it is such an important service that the Certified Cloud Practitioner exam will occasionally get into the weeds with it. You need to know that S3 buckets are made of objects that have keys. You need to know that it has incredible durability across all the storage classes, but that the storage classes are priced differently based on how available and quickly they respond. And you need to know that it offers features such as life cycles and replications and when you would use those. Okay, if you have any questions, reach out to me on LinkedIn or Twitter. I'll see you next chapter. Hello, everybody, and welcome back to AWS Certified Cloud Practitioner Bootcamp. I'm your host, Bill Bolden, and this is Other Related Storage Services. S3 is definitely the big one here, but there are lots of different ways you can store files in the cloud, and we're going to go over what those are now. One of the most crucial ways is EBS, the Elastic Block Store, and that is hard disk space as a service. Most importantly, it can be attached to EC2 instances to function as their hard disk or like their boot drive. As we saw in the example earlier in the EC2 walkthrough, they can be solid state or traditional hard drive based. It offers 5 nines of availability, and it can't be easily scaled later. It is not unlimited storage. So those of you who have formatted hard drives before probably remember that to make a disk and directory structure, you have to specify what the allotments and allocations for the file trees are. EBS kind of works that way. If you are making an EC2 and you provision it with an attached EBS hard drive and you ask for 100 gigabytes, and then later you need 200 gigabytes, you cannot expand the size of the EBS. It would require a reformat. You have to make a new, different EBS that is distinct, copy all the files over, and then remount that new EBS to the original as its hard drive. So a little cumbersome. However, it is generic disk space as a service, and so it's very flexible. A little less flexible, but very useful, is EFS, the Elastic File Store. It's not just abstract disk space. You can't put whatever you want on these bits and bytes. It is specifically file storage in a file tree, but it can also be attached to EC2s or Lambdas or ECSs like containers. It has 11 nines of durability, and it has 4 nines of availability, and it's pay as you go for how much storage space you consume, okay? EFS is a good way to think about things like, and I don't think this will be on the exam, but this is my experience, like mapped network drives, kind of. Like you have a different volume of files that you want to attach to some Lambdas or some EC2s, and it's a file directory structure. It doesn't have the flexibility of the raw bits and bytes on the hard disk that EBS does, but it's pay as you go and infinitely scalable, so it has a pretty different use case. Let's take a second to talk about Snowball. Snowball is actually a piece of hardware, which you can see in this great image here. It is a one-time way to upload as part of an on-prem to cloud transformation. So let's say that when I was working back at that place in 2012 that had the on-premises data center, that we decided it was time to move to the cloud. And one of the first things we have to do is get all our data up there. There would be terabytes and terabytes of data. You're not going to upload it over an internet connection. That would take weeks. The way you do it is you order a Snowball. It is this massive collection of hard drives in a case. It arrives in 4 to 6 days. You plug it into your network where it will be accessible using, much faster like Cat5s or whatever cables. Upload all your data into the Snowball, ship it back to AWS, and then in a few more days they get back to you and say, here's the S3 bucket and the contents are everything you put on the Snowball. So that is how you do a one-time data upload of on-premises to the cloud. Which takes us to the Snowmobile, which is an armored truck full of Snowballs. It can hold exabytes of data, and it is for truly massive one-time on-prem to cloud transformations. This is what you have to order if you are a massive Fortune 500 company that is too big for even the Snowball. If you are Verizon or something and you are uploading beyond petabytes of data to the cloud, you get the armored truck full of Snowballs. It seems niche and marginal, but last I checked, these are on back order 6 months out. Okay, the next thing you need to know exists is the AWS Storage Gateway. It is like a bridge between an on-prem data center and cloud storage. So let's say you're not ready to completely move to the cloud. You still want to run your web servers from your Dell server farm at your company's location. That's cool, but you do want the unlimited data storage of the cloud. AWS Storage Gateway is an encrypted and private bridge between the inside of your network and S3 that can cause those files that are stored in S3 to behave like they're a local network application, and it will cache frequently used files close to the edge inside your building, so you're not always going back and forth to the cloud. But it's sort of like your on-prem network is extending to the cloud. That's how an AWS Storage Gateway works. Okay, as far as the exam is concerned, those are all the other different ways besides S3 you can store data at Amazon. I do see questions a fair bit on each of these, so especially remember the difference between EBS and EFS. Other than that, though, if you have any questions, reach out to me on LinkedIn or Twitter, and I will see you next chapter for the most fun chapter of the whole training. Hello, everybody, and welcome back to AWS Certified Cloud Practitioner Bootcamp with your host, Bill Bolden. This is going to be the lesson on AI and ML. We're going to call it a shallow dive, not a deep dive, okay? Because, again, with this exam, the exam will test that you are conversant in what the offerings are, not the details of how they work. Again, I'm going to have to editorialize a little, especially with these services, because they vary widely in usability. As of the time of recording this particular chapter, it is October of 2023, and AI is growing by leaps and bounds every day. Whereas some of these services were ahead of the industry or groundbreaking 5-6 years ago and have since been eclipsed. And I'm going to try to help you tell the difference. Okay. Over here, you can see a list of the machine learning services. I'm going to talk about some of the biggest. SageMaker is their most advanced ML product, and it's close to a Jupyter notebook. Okay, so it's a place where you can run ML environments. I actually haven't used it because I am no data scientist. I am an engineer, but I have heard from my peers that SageMaker is a very good place to run machine learning. So as you can see here in the typical SageMaker workflow, we're talking about the nuts and bolts of machine learning here. They call them SageMaker notebooks instead of Jupyter notebooks, but you pretty much load in your data, run data analyses, and you get vectors and parameters and algorithms. You'll definitely want to take a separate certification course in Amazon Machine Learning if you want to go deeper on SageMaker, but that's a summary of what it does, yeah? Now, let's talk about some of the more special purpose ones. Code Guru and DevOps Guru is claimed that they can do code reviews and infrastructure reviews using AI. I have not known anyone who has used it and can comment on if it is good. Amazon Comprehend is a big one, but it has been left behind. So let's talk about Comprehend a little, okay? It is a sentiment analysis engine that came out in 2017. And I could say something like, boy, howdy, I sure do love O'Reilly trainings. The instructors are so smart, especially Bill Bolden. Unfortunately, he is short. All right? And it can run this text analysis and extract that the word O'Reilly was an organization and that the word Bill Bolden was a person with confidence intervals. And it can extract what the different parts of speech are, what language it must have been in, and where the PII that needs to be redacted is, yeah? As well as sentiment, right? It is 94% confident that this was mixed in sentiment, some good, some bad, right? I love O'Reilly trainings, the instructors are smart. Unfortunately, Bill Bolden is very short, so a mixed bag, right? Targeted sentiment, that the O'Reilly is pretty positive, the instructors are positive, Bill Bolden, neutral. Yeah, so anyway, here's the thing. This came out in 2017, and I used it all over the place for sentiment analysis. It's pretty next gen, right? Since then, since 2022, we've had true LLMs come out, the chat GPTs and bards of the world, the actual large language models. And you don't need to use this structured syntactical interface anymore. If you want to extract sentiment from text, ChatGPT is just light years beyond this, right? It knows about grammatical tricks, it knows about double negatives, everything in between. And instead of doing rules-based syntactic extraction, it's just another world. So I feel that this service has been kind of left in the dust by technological advancement, and that they should consider going back and just rewriting it to be based on LLMs instead of 2017 era syntactic analysis. My 2 cents, okay? Amazon Polly is their text-to-speech engine, okay? I find it was ahead of the curve a few years ago. It did pretty good synthesis of speech from text. Now, with the coming of Whisper by OpenAI and the entire product offering suite of 11 labs, I think it's a little bit left behind, but it's still competitive, right? So let's go ahead and just take a little stab here. Let's neural it up. We've got to go to Virginia if we want to use neural. Okay, that's Joanna. Hello, wonderful students. You are all very smart. Bill Bolden is your new friend. All right, let's hear this.
Hello, wonderful students. You are all very smart. Bill Bolden is your new friend.
there you go. So, mixed results, right? I think there's enough AI out there that can truly make human indistinguishable stuff, and you can do that voice replacement for specific people that I don't necessarily know you have to use Poly anymore, but it is still very affordable, and it was recently, among the best. It's just that the rest of the industry has moved on, okay? Speaking of which, let's talk about Transcribe. Same thing in the reverse direction, turns spoken speech audio into text. I've had really good luck with it, and I like its rates. There is no shortage of AI services right now that can turn audio into transcriptions, but Transcribe is affordable and supports 26 languages, and I'm still using it. Textract is their OCR product. I like it. It has a notable oversight that actually is driving me bonkers. This is neither here nor there, but a lot of documents have unusual layouts. It can do OCR of like bulk 8.5 by 11 text, but once you start arranging things in a grid layout or in columns, like a 3-column piece of paper, Textract loses track of what's happening and marbles all the OCR text together. So to me, that's a pretty good, great big failing, but it does do OCR well. And Translate, of course, is translation. It's what it says on the tin. It's very good. I feel like this is another place where the last 12 months advances in AI have left the old product behind, but translation was already pretty good. It didn't need the last year's worth of AI advances to become competitive. Translation has been good for years. So then there's a couple others. There's Comprehend Medical, which is Comprehend, but specifically for redacting health data. Deep Composer and Deep Racer are specific purpose, like Deep Racer is for automated driving, and Deep Lens is for automated image recognition. The big one, the big news, which is too soon to talk about, is Bedrock. At the time I'm recording this, in October 2023, Bedrock is new. It's only been out a few months, and it says this is the new AWS service for taking a foundational model and then layering your own model on top of it, which is, of course, the new game in town with AI startups. I have talked to some of my peers about it. It is too soon to say, okay? So, if you want to run in premises a base LLM that you then fine tune with your own information, Bedrock is the service that's supposed to be able to do that. I'm holding out until someone who I trust comes back to me and lets me know if Bedrock can really talk the talk and walk the walk, or if you just really want to license Bard or OpenAI's product, which are on the leading edge. And I will reserve judgment until I've had more of a chance to play with them. But in any event, that has been the shallow dive into some of the AI and ML offerings that Amazon gives you as part of its suite of web services. In conclusion, for many years, these were industry leaders, and I use them all widely. Every day, as the feature set of the industry leaders in AI continues to expand, I'm leaving the AWS services, which were written in a last generation way, behind in exchange for more offerings from Bard and OpenAI. But it's just going to be an arms race, and you'll have to check back with me in the future to see who's currently winning. I will always offer you my personal opinion. And of course, as far as the test is concerned, the AWS services are always the right ones. Well, thank you. Get at me with any questions on LinkedIn. I'm your host, Bill Bolden, and I'll see you in the next chapter. Hello again, everybody. Welcome back to AWS Certified Cloud Practitioner Bootcamp. I'm your host, Bill Bolden. This chapter is On Demand, Reserved, and Spot, 3 ways to buy resources. So the first way to buy resources is on demand. You pay for the amount of time that your server is running. If the server is stopped or off, you do not pay. It is expressed in a cost per hour, okay? So an example here you can see on the screen. As of the time of writing these slides, a C4.large server costs 3.8 cents per hour to run. So for a monthly cost, somewhere in the hundreds of dollars range. You can keep on-demand costs low by reducing the minimal Elastic servers needed to meet demand at any particular time. You can also turn servers off when they are not needed. For instance, you can turn off the development servers at the end of the workday when everyone goes home. The second way to buy compute resources is reserved. You pay a larger fee upfront to commit to pre-buying an instance for a term of either 1 or 3 years at a savings of roughly 40%. You then cannot reduce costs after the commitment, okay? So actually reserved and on-demand sort of are used side by side. A wise strategy is to reserve the servers you know will always be on. So we've talked a lot about elasticity. Here's kind of where it kicks in. Let's say you're running an Elastic Beanstalk pool of servers that is allowed to scale as low as 2 when demand is low and as high as 16 when demand is high. There will always be at least 2 servers running. So you should purchase 2 reserved instances because 2 of those servers will always be on forever, and you can get savings of about 40%. The rest you can pay for on demand so that when they're needed, you're paying for them, but you're not when they're not. And they don't need to consistently be the same two servers. So if you reserve a C4.large for 1 year, you are not reserving one specific C4.large. You are reserving the right to run up to one C4.large at a time without being billed for it. Okay? So you can spin down your C4.large and spin up a C4.large to replace it, and it kicks back in as your reserved instance. Again, it doesn't have to be a specific instance. It is the right to run up to that many at a time without being charged on demand for it. There's a third way to buy instances, which I use in my experience very infrequently, called Spot. Spot is a live bidding auction where you're okay with your server only running when the price of computing falls below a certain threshold. Okay? This is for stuff that every penny counts. So let's say you don't want to pay 3.8 cents per hour for your C4.large to run. You're only willing to pay 3.6 cents per hour. And you're okay with having your C4.large just not running most of the time. But if the cost of computing in the live auction environment gets cheap, they will auction it off to those who have put in the highest bids, and then those spot instances start running. Okay, so there's a lot of wiggle room in AWS since they have an economy of scale. They have lots of extra compute capacity to go around at any given point. And so if they have extra servers sitting idle, they'll go to the free marketplace, and the people who bid 3.7 cents per hour can have their servers run. And if those people get used up, the people who bid 3.6 cents per hour can have their servers run, et cetera, et cetera. Okay, more important than understanding the details of how this all works is understanding why you would use it. This will be on the exam. They would say, like, in what case would you use a reserve instance? So let's talk about it. On demand, first off, if you're playing or experimenting, on demand is great. You don't want to reserve, but you don't want to go bid for spot. So you just, let's say you're trying to make a new pool of servers for a new app you're spinning up. Go ahead and start a C4.large and just pay by the hour for it. Maybe something is temporary, like sometimes we have the production database server, which is obviously something that is always on forever all the time, and we use a reserved instance for that. But I need to temporarily spin up a historical snapshot to go back and get some data from a few weeks ago, and I only need that for a few hours while I extract the data from it and then come back. That would be a great case to spin up the database in the on-demand variant. And then the third example we already talked about, if you have an oscillating size Elastic Beanstalk server pool, reserve the ones that are always on demand the rest. Okay? So I went over a little bit of this in the last slide, but here is when you would use a reserved server. Again, in the Elastic Beanstalk case, for the ones that are the minimum, so that you're not paying full price for the servers that are always going to be there no matter what. And then, of course, for something like your production database, you have no reason to ever turn it off. It needs to be on at all times. You totally expect to use it for the next year. Go ahead and reserve the instance. Now for a more confusing one. When would you use Spot? Okay, I'm going to be honest here and talk about myself personally. I don't have a lot of use cases for Spot, working in the startups I do. But here's a case where you would use Spot. Let's say you have a large neural network machine learning model to train. You're working on the successor to GPT-4 or something. It's going to cost you 6 figures or even 7 figures in computing costs to process all your training data. You don't care when it gets done, okay? It can take months to train all this data. So it can happen during off hours, it can pause, etc. But even a slight savings on computing time would be significant. I'm going to ask for servers that are only on if the price of compute falls below 2 cents per hour. And if they don't get around to me taking my turn on those servers for a month, so be it. I'm really interested in that proportion of savings. That's an example of when you use Spot. All right? This has concluded the lesson on the difference between on-demand, reserved, and Spot instances. If you have any questions or you want to further your learning journey, you can always reach out to me on LinkedIn or Twitter. Hello, everybody, and welcome back to AWS Certified Cloud Practitioner Bootcamp. I'm your host, Phil Bolden, and this chapter is organizations and how they help you consolidate billing. All right. Essentially, what organizations are is several AWS accounts under one roof, okay? The AWS organization is billed like it's a single entity, but budgeting and appropriation is per account within that organization. They really like this on the exam, so definitely pay close attention during this chapter. Okay, here are 3 different ways I have seen organizations used. One is by environment. So you have an organization representing your whole company, but you have one sub-account, one AWS account within the organization that runs production machines and has its own budget, and another account that runs development machines and has its own budget. So you can track spending on production differently from spending on development. Another way I've seen it used is by department. So you separate out the budget for product to use some resources, as opposed to marketing and develop and operations, all of which have their own account. The third way I've seen it used is to separate out billing by developer. So for example, Christy has a budget of $100 for her AWS account. She can play with it. The organization pays for it, but you'll get warned if Christy's individual use of the AWS account is going over $100. Clayton has his own account with $100. This way, neither of them can run up a bill of thousands on their own, right? You'll never play the game of like, who created this C5.2x large server and left it running all month? That's all there is to that. Again, to recap, it's very important to understand that organizations are a way for multiple accounts to all live under a single billing entity and that they can be individually budgeted. There are a variety of different ways you can use this. They will ask about it on the test, but that's really all there is to it. As always, if you have any questions about this, find me on LinkedIn or Twitter. Hello, and welcome back to AWS Certified Cloud Practitioner Bootcamp. I'm your host, Bill Bolden. This chapter is support, how to get help with your account and how you pay for it. All right, let's talk about the basics of AWS support because there's a lot going on here and it will all be on the exam. AWS support is available in 5 different tiers. We're going to talk about them in detail because sometimes they will ask questions about them in detail. It has a different SLA, which is the response time, service level agreement, which is how long it takes them to answer your request, guaranteed, depending on the severity of the business impact. So if you send in a case saying, I have a billing question, the SLA applies a certain way. Depending on your tier, it might be 24 or 48 hours. If an entire region goes down and your website is down and all your services are down and you're losing money with every second that goes by, you want a faster SLA. You want them to know that they are guaranteed to respond in 15 minutes or less. The different tiers will offer different SLAs. Okay, so support uses cases that are resolved individually. And there are 3 methods of interacting. You can either put in your phone number and have AWS call you. You can start an email-based ticket, or you can live chat with a representative. I personally endorse live chatting with a representative wherever applicable. I have probably gone to AWS support several hundred times in the last 4 to 8 years that I've been building all these startups. And I really feel that even though the SLA says they don't have to respond for 24 hours when you send in a ticket, if you ask for the live chat, somebody responds within 5 minutes every time. I really like it. But let's go on to the details about the 5 tiers. Oh, wait, no, just a moment. First, let's talk about Trusted Advisor because it figures into every tier. Trusted Advisor is an automated service that identifies common mistakes or warning signals in your AWS account. They are really big on Trusted Advisor over at AWS. I'm going to editorialize for a minute. This is my own personal opinion. But I have found Trusted Advisor to be of limited usefulness. At all my startups, it always recommends like the same 2 things and passes the other 50 checkpoints. The number of checkpoints Trusted Advisor provides to you is dependent on your plan. All the tiers have different amounts of Trusted Advisor you have access to. But in the past, I've always run Trusted Advisor and been like, yep, same 2 warnings as always. Everything else passes. That's been my experience. That's between you and me. But on the exam, they really like Trusted Advisor, so know what it is. Okay, first tier of support, basic support, the default. When you make an AWS account, you are put on basic support automatically. It only covers customer service. They will not help you with their functionality or their features or configuring anything on AWS or hacking or your account. They will only help you with the kind of things that any customer service rep would. Like, I need to change my credit card on the file, or I need to update my address, or I have a problem with my last bill. You still get access to the basic level of Trusted Advisor. It's free. And in my experience, they can't help with very much aside from very basic billing. You can dispute your bill. You can change your credit card, basic customer service level things. If you have any questions about the functioning of AWS whatsoever, they're going to pressure you to sign up for a higher tier of support. The first tier of support above basic is called developer support. It costs either $29 a month or 3% of your bill, whichever of those 2 numbers is greater. They promise a 24-hour response time SLA for general guidance and a 12-hour SLA for system impairment. Okay, you get general architectural guidance. I use developer support at most of my startups because it is cheap. And for the general guidance, I usually can afford to wait 24 hours. I will say that there have been times, personally, that I've been on developer support and I have groaned at the 12-hour SLA for system impairment. Sometimes US East 1 goes down and your servers are down, and it kind of stinks to not hear back for 12 hours about it. But developer support gets me by. The second tier of paid support is business tier support. It is either $100 of a month or this formula of decaying returns on the amount of your bill, whichever is greater. I'm not going to say it. You can read it on your screen. You have access to the full suite of Trusted Advisor checks. And they will start giving you what they call architectural guidance, where they will advise you on how to architect your systems to use AWS to the best of your abilities. General guidance is 24 hours, system impaired is 12 hours, production system is impaired is 4 hours, and production system down is 1 hour. So this is where if you've hit stride in your company and your startup is off to the races and working 24/7 and your servers need to stay up, you may want business tier instead of developer tier. Developer tier is more for when you're building. Business tier is more for like, hey, if my servers go down, I need to be able to yell at somebody and hear back within an hour. Okay, now there's a big jump to the third tier of paid support, enterprise on-ramp. All of a sudden we go from $100 a month to $5,500 a month, or 10% of your bill, whichever is greater. You have access to the full suite of Trusted Advisor. You will get what is called a consultative review, where someone will come and review your system for you and give you personalized architectural guidance. With the previous tier of support, you got generalized architectural guidance, but you had to ask. Now they're coming and doing it for you. You will have access to what are called technical account managers, or TAMs. They are people who will get out ahead of things to help you with stuff proactively. And you can see that the response times are the same as they were for business tier, but there's a new, even more urgent level of SLA. Business critical system is down, you get less than 30 minutes. Now we're going to take another big jump to full enterprise tier support. $15,500 a month, or a big proportion of your bill, as according to this formula. Full suite of Trusted Advisor. Trusted Advisor checks that can be curated by your team. You get the architectural consultative review. You get the TAM providing proactive guidance. And the new SLA for business critical systems going down is less than 15 minutes. All tiers include these other features. They all have some level of Trusted Advisor. They will all help you with anything customer service related via the 3 different communication mediums. They all offer you the personal health dashboard, which is like status.aws.amazon.com, but localized inside your account so that it only reports on things that are down with the services you use. The personal health dashboard is pretty cool. Because Amazon Web Services is made up of 200 to 300 different web services, there is often something somewhere in one region that is down. But that can be a flood and a deluge of information, because it doesn't matter to me very much if Elasticache is down in EU West 2 right now. So, I'm not running servers there or using Elasticache there. The personal health dashboard is an area you can visit that will report on anything that is down that you use in a region you use. Okay, you also have access to the communities, which are like forums, the documentation, and white papers. I know this might seem like obvious, like of course you have access to the documentation, but it is considered a part of AWS support. And so if an exam question asks, which of the following is not a feature of AWS support, and one of the choices is documentation, you don't have to pick that one. They consider their documentation and their forums to be part of support. All right, that concludes the lesson. If you have any questions, you can reach me on LinkedIn at Bill Bolden or Twitter at DownUpRight. I would just like to close out this chapter by saying I injected a lot of my personal experience into the reading material because I have worked at so many AWS startups over the years, and I have a lot of experience with AWS support. That will not be on the test, but I'm also trying to educate you and help you learn from lived experience as we go. So review the slides to see literally what's on the test, but when you go to put it into practice, consider my advice. To recap, people respond a lot quicker through live chat than they do through phone or email. Developer or business is good for startups, but enterprise is necessary for things that hit scale. There are big price jumps on the way to enterprise. Trusted Advisor is really popular among the exam questions, although I found it to not be that useful in practice. And there was one more thing I was going to say. The last thing I wanted to add is that it can be useful to actually flashcard those 5 slides of what's in each of the 5 tiers, because I have seen on the exam questions that literally ask, I want to buy support and I know that I need a TAM, technical account manager. What tier of support do I need? And there's no way around answering that question other than having memorized what's available at each tier of support. So it can be worth it to flashcard. Okay, that concludes the lesson. Thank you, everybody. Hello, everybody, and welcome back to AWS Certified Cloud Practitioner Bootcamp. I'm your host, Bill Bolden, and this chapter is budgets and TADs. The most important thing you need to understand right out the gate about budgets, and this is like non-negotiable, they can't actually stop you from spending money, okay? This is something that has led to a lot of horror stories. But if you set a budget for $100, it will track your spending. It will alert you as you approach your $100 spend point. It will tell you to change course, etc. But it cannot cap you at $100 and actually stop you from spending more. The budget does not actually do anything. It is a monitoring tool to keep your eye on. It will notify you if things go awry. But what you cost AWS is what you will be billed for. So if you have a budget for $100 a month, and you decide to make a C5.4x large server and leave it running, you will get a notification when you've spent $100. It will tell you, and then it will go ahead and run up a $500 or $1,000 bill by the end of the month anyway, despite your budget. This is not how a lot of people would intuitively expect budgets to work, so I have to be very clear about it. You can blow through your budget, but a budget will keep you informed and in the loop on the way. Okay, here's an example of where you would use a budget. For the last few months, my AWS bill has been around $2,500 a month. It has been as low as $2,300 and as high as $2,600. If it was to go over $3,000 though, something has gone wrong. I will institute a budget for $3,000 and be warned if my bill surpasses this amount. This happens all the time at my startups. You sort of settle into a comfortable level of spend on AWS while business is steady, and you're like, okay, I'm used to the bill being roughly this amount. Let me know if anything changes. Okay, so here's an example from my personal AWS account, which is sort of a dumping ground for personal projects. I am very used to spending $60 a month because that is all my random one-off servers and projects that I have put together. And I set a budget for $100 because I would want to know if it ever approached $100. And you can see here that it shows me how much I've used so far this month and where it is forecasted to end. This screen cap was taken towards the end of the month. So it can forecast based on your trajectory where you're going to end up. There's a concept called savings plans. It is an alternative to reserved instances that does not care about region or type of instance. It is more flexible than reserved instances, and it is newer. However, the test has not been updated to reflect that savings plans are a newer, better way to do reserved instances. So let me highlight the difference. A reserved instance is a promise to prepay for one server of one size to be running in a particular region. You can prepay for a year's worth of running an M4.large in US East 2. Okay? A savings plan is a more general prepaying to promise to run a certain amount of server across any region, across any type. So you can audible halfway through the year if you wanted to, and be like, we're actually going to switch from M's to T's and put them in US West 2, and your savings plan will still apply. This means savings plans are generally preferable to reserved instances because they're more flexible. But the test has not caught on to this yet. They will still ask you questions about reserved instances, so be prepared to answer those. But if you could ask what a savings plan is, that's what a savings plan is. When you go to make a budget, there are helpful templates for some of the most common use cases. I'll go through them real quickly. You can easily create these 4 templates of budget. A zero spend budget notifies you as soon as you spend any money at all, which is useful for someone experimenting with the free tier of AWS who wants to not spend a penny of real money. A monthly cost budget is like the kind I showed you on the last slide, where you set a $100 or $3,000 limit and say, if I'm forecasted to spend more than this, let me know so I can change course. A daily savings plan coverage budget is if you have prepaid for services you could be running under a savings plan, but you're actually not utilizing that level of resources, it will alert you. For instance, you have prepaid for a year of running servers somewhere with a savings plan, but you only ran 2 servers today when you could have run 4. You're wasting money. And the same thing goes for a daily reservation utilized budget for reserved instances. I have prepaid for a year of running 8 T2 mediums in US East 2, and I only used 6 today. It will alert me to be like, you could have been running 2 more. You paid for them. Let's talk about tags. Tags are very much used the same way you use organizations. They help you separate out different costs and spends. So you can set budgets for specific tags. All resources you can create in AWS of all types support free-form tagging. You can make a server and tag it with the word development. You can make a SQSQ and tag it with the word Christie. You can make a DynamoDB table and tag it with the word customer 5. Then when you go to make a budget, you can actually sub-budget for certain kinds of tags. Like, I want to set a monthly alert if I am forecasted to spend more than $500 on things tagged with Christie. I hope that all makes sense. Although tags and organizations are 2 very different tools that do completely different things, they are often used to accomplish the same end, which is separating out and differentiating spend and budgets for different purposes so that it doesn't all get lumped into one giant, messy omni-bill. Here on the screen, you can see an example of how you can filter by tags. It's included with every kind of budget. There's one more thing I want to go over with budgeting. There's a tool in Amazon called QuickSight, which I am personally not a big fan of. It is a BI tool that can do a lot of things. It is most similar to Microsoft Power BI or other kinds of dashboard tools, as you can see on your screen. There are lots of tools like this in the marketplace. AWS's particular tool is called QuickSight. And one thing they particularly like on the exam is reporting on your budgeting data on your QuickSight dashboard. So keep an eye out for that. QuickSight in general will not be on the exam. and they won't ask questions about the functioning of QuickSight. However, they do particularly like the use case where on your BI dashboard that you make in QuickSight to monitor your whole business, one of the things you're monitoring is your spend. So just remember that. At the enterprise tier, you get what's called access to the concierge team, which, remember, there's that big jump from $100 to $5,500, and they start working with you proactively instead of reactively. One of the things you get with the concierge team is a team focused on lowering your bill and working on your budget and cost setup so that you spend as little money as possible. All right, now I'm going to show you the AWS pricing calculator. It is a tool that will be on the exam. The AWS pricing calculator is a tool that lives in AWS where you can put in the services you wish to run and research how much they're going to cost you. So let's start real simple with an EC2 perhaps. Let's configure a new EC2. When you pick your tenancy, you're choosing whether you want dedicated servers to yourself or you're willing to run on the shared virtualized hardware. You should always run on the shared virtualized hardware to get the most savings and make the best use of AWS. If you are one of the rare cases, such as Department of Defense work or something, where you need, for legal or compliance reasons, to guarantee that they have a server set aside just for you that belongs to you and no one else, you can make them dedicated hosts. That is vastly more expensive. And instead of things that cost pennies an hour, you're looking at thousands of dollars a month. But let's go with shared instances. If you want Windows, the cost of buying and licensing Microsoft Windows is folded into the price you pay for the server. So I'll run a Windows server, and I want 10 of them. And let's say I want them to be T4 or T3 largest. And it asks if you're prepaying with reservations or paying by the hour. Let's go with on demand. Okay. This is an $800 estimate to run my new server farm of 8 T3 largest. So you can get a perfect and accurate forecast of exactly how much the resources you're about to use are going to cost you. Notice, by the way, at $800 per month, if I wanted to reserve my instances, it would cost me $6,600 per year, which, if you do the math, is more like $500 to $600 a month instead of $800. So that's where those savings kick in if you're willing to prepay for a year. That concludes this chapter. As always, reach out to me on LinkedIn or Twitter if you have further questions, and I will see you in the next chapter.
to welcome you to my course, AWS Certified Cloud Practitioner Complete Video Course. This course covers the CLF C01 version of the exam released in 2022. AWS certifications are among the most sought after in the technology sector, and the certification exams cover a wide range of fundamental AWS services and technologies. Before we get in, the next talking point in the cloud value proposition is the word agility. And this is a term that I associate with the primary reason why companies and organizations should want to move to AWS. The idea that you can go to market faster, experiment faster, fail faster, without quite the cost investment that would be required for an on-prem data center is powerful. One way that AWS makes this possible is the concept of democratizing advanced technologies. And this is something that is discussed in more detail in the well-architected framework. But the short definition is that AWS takes on the operational burden of becoming experts in certain softwares and workflow to match your demand, and it implies automation and redundancy of those resources. Scalability is a little bit simpler. It's more designed for the addition of resources and recognizing where the ceiling is, where you can no longer add more resources for a particular use case. Scalability can also include vertical scaling, where rather than adding extra servers, as an example, that would be horizontal scaling. Vertical scaling would be opening up one server and just putting more CPU and memory into it. And so it does not necessarily imply automation, although self-healing is definitely possible when you consider scalability. Our next term is global reach. And if you look at the global infrastructure of AWS, from data centers to availability zones to regions, you'll realize that they have quite a solid placement in both technology and population centers around the world. And with the addition of newer scopes like local zones, they can go even further to help customers meet their requirements around data residency or proximity to various clients or other infrastructure. Our final point in the cloud value proposition is the term economy of scale. AWS is able to provide very competitive pricing on the various services and features. And one reason for this is that AWS, because of the scale in which they operate, compute, network, and storage, that they don't have to pay the same prices that the rest of us around the world would have to. And because they're getting their infrastructure for lower cost, they can then turn around and provide it to us as the customers at lower cost as well. Welcome to our first question breakdown for this cloud practitioner exam. And then we'll take a look at the answer choices. And then we're going to spend some time, one correct answer for us to choose from. Which of the following are you pretty sure at this point? Let's see if there's something better. C, elasticity. The ability of a system to increase and decrease resources. Hey, that's better. And usually horizontal scaling to match demand and implies automation. Well, this is really close to what we saw in the question. And there's nothing explicit in this definition that would eliminate it as a correct answer choice. But even if we think we have the correct answer, we still need to look at all the answer choices to make sure that we know why the wrong answers are wrong. Let's look at answer D, economy of scale. What is that? Well, AWS has a lot of infrastructure resources. That means that they can provide competitive pricing to customers. This doesn't elasticity. How do we define business value? Is it time spent generating revenue? Maybe. Is it the reduction or elimination of tasks that don't contribute to agility? Yeah, you can include that too. As we go through the rest of this course, we're going to talk quite a bit about this term business value. It does not have a significantly higher temperature than the ends, and that you have enough air conditioning and power and space for all the hardware that you've purchased. None of these tasks are going to contribute to the agility of a company. Now let's compare that to tasks that would be required to manage cloud infrastructure in AWS. Well, we need to spend time figuring out how to make our costs visible and attributable to the various workloads. We look into horizontal scaling and design our architectures around that. We spend time on automation for both provisioning and the deprovisioning of resources, as well as the operations and the lifecycle in between. And we spend time right-sizing based on recommendations which may be generated using machine learning. As you can see, there are still a lot of tasks that have to be performed in a cloud infrastructure as compared to on-premises data centers. Is it more or less, or is it maybe close to about the same amount of time overall? In my opinion, it's close to the same. But the activities that you are performing, all of them have the ability to improve the agility of your company and to increase the overall business value of the infrastructure that you're deploying into AWS. What else can we get in terms of benefits from managing our infrastructure in AWS rather than doing it on-prem? Well, as long as we take the time to figure out our KPIs and set up tags and so forth, we get full cost transparency. We know everything that's going on that's generating cost. We can achieve mechanical sympathy, which means we can select services and features in AWS that exactly match our requirements for our applications. We have the ability to switch technologies as our demand changes or as new technologies become available. This speaks directly to the agility of the company. If we design our infrastructure using cloud-native concepts and strategies, then our infrastructure can recover automatically from failure, and there may not even be an interruption to the users. We have the ability to experiment. This leads directly into that previous step of switching technologies as demand changes. Well, if you don't know what other technologies are available, it's going to be really hard to be able to switch to them later. And our last point here is the ability to deploy globally without having to manage data centers. We saw all those tasks that are required to maintain a data center and how none of those contribute to business value or agility of the company. So if we can get all the benefits of a global infrastructure without having to do all that work, that's a huge benefit and also contributes to that business value. Welcome to our second and final question breakdown for this lesson. Let's go ahead and follow the same procedure that we did with the first one, where we're going to read the question, we'll look at the answer choices, and then we will go through each of those answer choices in order and determine how well they match the requirements that are laid out in the question, with the intent of eliminating first the 3 incorrect answers so that the only one left must be the correct answer. And if we find the correct answer along the way, all the better. When drafting a justification for migrating to AWS from an on-premises infrastructure, what would be a task that cannot be eliminated after the migration is complete? This is an interesting question, and the word not is important, and that's why I went ahead and made sure that it was put in capital letters. It means that we're looking at an inverted question, which tells us that 3 out of the 4 answer choices would be tasks that can be eliminated after migration is complete. So we're looking for the only one that we're still going to have to perform even though we're in AWS afterwards. So let's go ahead and take a look, starting with A. OS patch management on virtual machines. Well, we can make some assumptions here. EC2, as an example service in AWS, is one of the most commonly used. And it gives you an actual operating system. It's a virtual machine service. AWS manages a hypervisor. The customer manages the guest operating system. If you, as a customer, are still going to be using discrete operating systems on virtual machines like EC2, you still have all of that OS management. All of those tasks are still your responsibility. We may have found our correct answer, the first answer choice. But let's go ahead and make sure we can eliminate the other 3 before we're sure. B, monitoring power and temperature. You definitely don't have to do this in AWS. AWS owns the data centers. They manage them fully. You don't even have the ability to tour a data center as a customer. And so environmental controls are not going to be your responsibility. C, repairing broken power supplies. Well, since AWS is managing the entire data center, all that hardware infrastructure is still their problem. And so if a server runs into an issue where you have degraded hardware, broken hardware, that sort of thing, it is fully on the provider, AWS, to be responsible for replacing those. And our final answer choice is D, testing the generator backup power periodically. Now, this is something that you would be doing if this was an on-premises data center, but as we've established, AWS owns and operates those data centers, and you don't even have the ability to walk into them physically, much less perform any of these environmental management controls. And so as we look through these answer choices, that first one that we saw, A, is a set of tasks we still have to perform in AWS, but the others are all related to data centers directly and are no longer the customer's responsibility. So our correct answer for this question is going to be A. Lesson 4 covers the introductory concepts for cloud economics. We will do a deep dive into the term TCO, or total cost of ownership, and explain how this is very different in an on-premises infrastructure versus being in AWS. We will discuss CapEx and OpEx financial models and how AWS can provide cost benefits beyond just looking at the monthly bill numbers. If we're going to properly discuss cloud economics, we have to cover some foundational concepts first. One of the most basic of these foundational concepts is TCO, which stands for total cost of ownership. Now let's go ahead and kind of define what total cost of ownership means in the context of on-premises data center environments. And the first way we're going to define it is going to be based on what many companies actually consider to be this definition of TCO. So let's start first. Total cost of ownership, as the name suggests, should mean all of the different elements, all the bits and pieces that are required as the ownership lifecycle of some set of hardware is concerned. And we can start with the data center itself. The brick and mortar building, the flooring, the ceilings, the walls, the environmental stuff that we put in there like air conditioning or power, those sorts of things. Cable management might be included in that data center. We're going to come back to the actual costs of this in just a moment and just say that most companies are going to say, well, we bought our data center 10 years ago. The building's already paid for. There's no further cost that needs to be calculated. Next, we have hardware, primarily compute hardware. All of the servers that we buy with CPU and memory and disk, all those pizza boxes that get stuffed into racks somewhere in the data center would be considered this hardware, and there are going to be costs associated with those as well. Next, we have storage. Storage might be included as part of the server or compute hardware, but oftentimes storage is considered a completely separate line item because we can buy storage appliances that don't really have anything to do with CPU and memory explicitly, and they operate independently from the rest of the compute infrastructure. Finally, we have the network hardware, individual network cards, switches, routers, and so forth. This might even include load balancers and VPN concentrators. All of these would be included as part of our network infrastructure. And so if we think about traditional on-prem based organizations, if they have a chargeback model whereby the IT team is responsible for paying for everything, and then they charge back to other organizations based on their percentage of usage, what variables do they consider? Well, they probably consider a nominal charge for taking up a spot in a rack in a data center. There would obviously be charges around purchasing servers, maybe using a percentage of storage, or even a nominal charge for using up a port on a switch somewhere in the data center. But does this include everything that should be part of that total cost of ownership calculation? There are a lot of other variables that would be part of this, including, can you calculate the cost of every watt of electricity or every ton of air conditioning? There are charges associated with those that could be split up and charged back to the individual consumers. Every square foot or square meter of space in that data center, even if it's already paid for, you're still using it over a period of years, there are still costs associated with that. What about backup power, generators, testing those on occasion, all of the spare parts that you need to have sitting around a data center for disaster recovery purposes? And then we get into the rest of the hardware, like having extra servers, just in case, the cost of dealing with broken hardware. With storage, how many spare disks do you have sitting around on a shelf that you aren't using because you want to make sure that if something fails, that you can replace it quickly? Network hardware is going to have time associated with making sure firmware updates are applied. All of the hardware is going to have maintenance contracts associated with it. And everything that we've talked about up to this point is going to be associated with a certain human cost in terms of time spent to keep everything up and running. And if your organization cannot calculate the true cost of copying a gigabyte of data from server A to server B, or the cost of pushing a terabyte of data out to an external partner, the cost of maintaining currency on all the firmware versions across all of your disk controllers, if you can't calculate that, then you don't truly understand the total cost of ownership. And what we're going to find out is that AWS, they do calculate these numbers down to the most granular values imaginable, and they pass this on to the customer. They present it to you in that granular form so that you know exactly what you're paying for. And as we go further and further into this conversation, I'd like to kind of have you thinking ahead that you're not calculating the total cost of ownership properly. That's really the most likely scenario coming from an on-prem data center. So when you move into AWS, if it appears like it is suddenly shockingly expensive, it's not because that's the truth of it. It's because you are not calculating how much your infrastructure cost before the move. Our next discussion in the concept of cloud economics will be to cover the contrast between capital expenditure and operational expenditure. Capital expenditures, or CapEx for short, is going to represent the financial model that we use primarily in on-premises data centers for a lot of the purchases. And there are some standard principles that go along with it, like upfront payments for hardware, assuming that maintenance contracts are going to be part of that payment. We amortize the value of the hardware over time, usually 3 or 5 years, until it drops down to where it's technically worth 0. And at that point, you make a decision. Do you want to continue to pay maintenance contracts, or does the hardware get fully retired? Or does it get moved to a non-production context? With capital expenditures, you own the product when you're done paying for it. And there is a very predictable cost that works well with yearly budgets or semi-yearly budgets. Operational expenditures, or OpEx, or variable expenditures, are almost the complete opposite of capital expenditures, in that it is a cost that you have to pay many times on an ongoing basis, like through subscriptions. It is perfectly aligned with AWS in that it's pay as you go, that when you use more, you pay more. When you use less, you pay less. This might be the most important point that we cover in this entire conversation around cloud economics. When you work in an on-prem data center, very rarely is any thought given at all to how much operations themselves cost. We think about purchasing hardware. We think about getting it all set up initially and ready to go. We think about the retirement. We think about the maintenance contracts. But what about every single operation that is performed on that server, or virtual machine, or storage appliance over time? Even in an on-prem environment, those have a cost associated with them, but we don't normally calculate it. AWS does. And that's what we'll find in this operational or variable expenditure model, that we are being explicitly charged for operations. And that these charges, because operations don't always happen in a regular cadence, can be variable and often unpredictable. Let's talk about the 3 primary principles of cloud economics. The first of these is called pay-as-you-go, and I've mentioned it here and there up to this point in the course. It means you can adapt to changing business needs. It means you can reduce or eliminate the time spent on forecasting what your costs are going to be and how much capacity you need. And it means you don't have to over-provision. In an on-premises data center environment, you have to buy more hardware than you're actually using. That is inherently a waste of money. Well, in AWS, that is not a strict requirement anymore. Our next principle is called save when you commit, and this is the opposite of pay-as-you-go. This is where you take advantage of commitments or contracts that you sign for usage of a certain amount of resources so that you can get a discount on those same resources. And you can do this using reservations, savings plans, and those commitments are for either 1 or 3 years, depending on the way that you decide to purchase. We are going to spend a lot more time in our final question domain, more, are using more resources in AWS. There are certain types of resources that have tiered pricing or volume-based discounts, so that the more you use, the smaller the cost on the individual unit of whatever you are working with. This tends to be concentrated in 2 different areas in AWS: storage and network traffic. This is our first question breakdown for this lesson. And in my opinion, this is a great example of a question that is extremely straightforward, with a short question, short answers, and requires fact-based memorization of terminology in AWS. So let's go ahead and take a look at our question. Then we're going to go through our answer choices one at a time and figure out which ones we can eliminate so that we can deliver the correct answer. Which of the following is not part of AWS Cloud Economics? If you're reading that quickly, you might miss the word not in there. This is another question inversion, and I did not highlight the word not because I want you to be looking for it from this point forward. What this means, if we go ahead and invert, one really interesting cost advantage of being in the AWS cloud is around compliance. And this is one that's difficult to quantify. But what do I mean by that? Well, AWS is going to be responsible for the various compliance frameworks for the AWS data centers and the services themselves and the features within the services. What does that mean for you? Well, it means that your compliance scope has been vastly reduced. All those controls that you would have to be responsible for if it was your data center, if it was your service API endpoints, if it was your infrastructure, are no longer entirely your responsibility. That can potentially be a huge cost savings when it comes to implementing those controls, because you can simply say, we're in AWS, here's a whole bunch of the controls that are now check, 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 they're done. And that absolutely saves money. Another way that you can achieve cost savings by working with AWS is by preferring managed services. And while these might appear to be slightly more expensive if you just look at the monthly bill and all the little granular details, what they're doing is they are reducing KTLO tasks, which we've talked about a little bit earlier. And so here's an example. You could implement a relational database on a couple of EC2 instances, and you can set up replication on your own. And then you're responsible for the entirety of the operational overhead from that point forward. Backups, the replication, software updates, failover, restores, recovery, all of that is your responsibility. And if it breaks in the middle, like what if your replication stops working and you can't get it running and you have to re-provision your replicas? That's entirely on you. There's no responsibility on the part of AWS if you did all this with EC2 instances. Instead, maybe you should look at deploying the same relational database using RDS. And not only does RDS absorb all of that operational overhead, you still have the flexibility to initiate tasks if it need be, and you get horizontal scaling out of the deal. Another example, let's look at an application tier. Let's say you have containers on things like the deployment of updates, OS updates, even rollbacks. All of this is your responsibility. These are KTLO tasks. The best you can hope for is that you didn't break anything. Instead, maybe look at using ECS or EKS and deploying using Fargate as using auto no longer EC2 instances. A third example would be based on the implementation of a shared file system. Let's say you want to create NFS shares on EC2. And let's say that you further realize, hey, we would like to keep that data in the same AZ as much as possible. So you deploy parallel infrastructure, one server in each AZ with the disk space on it so that you can share it out to the other resources in those same availability zones. What are you responsible for? Looks a lot like the database list backup. How do you deal with synchronization between or any kind of audit work? And not only is this going to take on all of that operational overhead, it is a region scope, same VP on top of that. For this lesson, for infrastructure. This is another inverted question where I've used the word not. That means that 3 of the answer choices will reduce the total cost of ownership, or TCO, for the infrastructure. We need to think about our definitions of total cost of ownership and all that TCO can include, that we want to make sure that we're keeping track of things like operational overhead. Now let's go through these answer choices. We'll start with A, choosing EFS for a shared file system. Well, we know that EFS is serverless. We know that it is region scoped and automatically replicates our data into multiple availability zones within a region. It is fully elastic, so we don't have to worry about provisioning a size of a file system or anything like that. And because a lot of that traditional infrastructure level operational overhead is simply gone, it's delegated to AWS, this would actually reduce the TCO over deploying a shared file system by hand. What about B, using EC2 to host a Java application? EC2 is just a virtual machine. And if you were using a virtual machine on premises versus EC2 in AWS, there's not a lot of difference there in terms of the operational overhead if you take away the underlying hypervisor and data center infrastructure. And so there may not be a lot of benefits to doing this from a TCO perspective. And AWS has other offerings that can execute Java code with more efficiency than EC2. So this might actually be our correct answer. We still need to look through all of the answer choices to verify that. C, using RDS for a MySQL database. Well, this is going to be kind of similar to answer A, where we talked about shared file systems, but now we're talking about relational databases. And this is a great example of a platform as a service offering by AWS that takes on a lot of that operational overhead that customer would normally have to do to keep a relational database up and running, and simply absorbs that into the service. Backups, replication, failover, updates, and so on. So this would actually reduce TCO. What about our final answer, D, deploying a NoSQL table in DynamoDB? Well, DynamoDB is actually further along the evolutionary scale than even RDS. It's a software as a service offering by AWS. It's entirely serverless. It's designed around NoSQL key value data. And AWS assumes almost everything in terms of the operational overhead. There's not even a concept of CPU or memory or anything like that with DynamoDB. It just works. So after looking through all of these answer choices, A, C, and D absolutely reduce the TCO over a self-managed infrastructure. B is the only one that's pretty questionable, and so that's going to be our correct answer. In lesson 5, we'll talk about the principles of being well architected. This lesson will be divided into 2 discussions. The first of these discussions is specifically focused on simple design principles. The second and much longer discussion will introduce the AWS well-architected framework and its 6 pillars. What we're going to do is we're going to break it up into a small number. It means that we have automation in place that allows us to create a full-size environment at any given time, which we can then use for testing. And so that's going to lead us a little bit deeper down that rabbit hole of, now we need infrastructure as code. We have templates that we can use to deploy these environments. We can apply parameters to make them unique at any given time. So we create this infrastructure, use it for testing, and then simply delete it when we're done. And that's going to follow along with that pay-as-you-go strategy for cloud economics. Our third principle is automate to make architectural experimentation easier. This actually follows that second principle pretty well with the idea of using automation, whether it's infrastructure as code or other types of programmatic operation, using the AWS command line, using SDKs, writing scripts. And this allows us to create infrastructure temporarily, and maybe we switch out service A for service B that performs the equivalent tasks, and then run a performance test to see how they do. Our next principle is to allow for evolutionary architectures, and this builds on each of those 2 previous principles. By decoupling our infrastructure, meaning we separate out the various application tiers, it means that we can use different technologies, different services, different features for each. And by properly decoupling and using asynchronous communication, load balancers, message queues, message streams, and so forth, it means that those individual application tiers can be replaced without a lot of effort on the part of the previous tiers to understand what changed on the back end. Our next principle is to drive architectures using data. This goes back to the concept of mechanical sympathy, where rather than picking from a really small number of technologies and then we go back and change our requirements, AWS has a service or feature that can meet each of our requirements exactly. And if we can define our requirements using objectively obtained metrics and data, it's going to make it a lot easier to create a cloud-native infrastructure that will behave according to our design. Our final principle is to improve through game days. And this really crosses over pretty heavily into the concept of DevOps.